Hello and welcome to Empowered Learning. This particular lesson will be the first of many lessons about permutations and combinations. What we want to do in this particular video is introduce what a permutation is versus what a combination is. We also want to look at what the formulas are and just get a general understanding through a concrete example of what a permutation can do and what it is used for versus a combination and what it is used for. So in general, when we talk about permutations and combinations, what we're really trying to do is count a large amount of something without actually having to count it by what we call brute force. And so what we mean by brute force is, let's say we wanted to group, let's say 15 things in groups of 2, and we wanted to figure out how many groups would that be. So we would take 2 things and then group them, and then let's say A, B on going forward. So we'll take A and B and group it, then A and C and group it, then A and D and group it, A and E, A and F, A and G, and then we'll just keep on doing that till A is paired up with the other 14. And then we'll go on with B and do the same thing, and then go on with C and do the same thing, okay? So of course, that would probably take a long time if we're doing 15 things put in groups of 2 to see how many groups that were. So imagine if we had 152 things in groups of 2. That would take an even longer time. So of course, counting all those one by one is what brute force is called. And of course, what we want to do is find patterns to where we don't necessarily have to do the physical counting anymore. And so hence, that's why we use permutations and combinations. Now, in general, we see that whenever we deal with a permutation, we're trying to do grouping of things where order actually matters. Whereas with combinations, we're trying to do grouping of things where order does not necessarily matter. And so we'll go ahead and kind of dig into each of them to see how they're alike and how they're different. So let's start off with the permutation. So a permutation is grouping when order matters. And so we say that when we do the permutation of something, we want the total number of ways in things can be grouped R at a time, okay? And so what we mean by order actually matters is if we were listing a group with, let's say, 1 and 2 in it, if 1 is listed first and 2 is listed second, then that is not the same as if 2 is listed first and 1 is listed second, okay? And a great example of that is whenever we plot points on a plane. So of course, if we put the point 1, 2 on the graph, that's going to be in a different location than the point 2, 1 on the graph, because we know that this 1 right here means that we go 1 unit in a positive X direction and then up 2 positive units in the Y direction. Whereas for here, we go 2 units in the positive positive X direction first, and then 1 positive unit in the positive Y direction, okay? Now, here is what the formula is for permutations, and we read this as the permutation of n things taken R at a time, or n things grouped R at a time. And so this is how we compute this using factorials. If you're not familiar with what factorials are, please check out my video on factorials to sort of give you a primer on what they are, how you use them, and how you use them to evaluate expressions, okay? So here we have n factorial divided by n minus r factorial, okay? And so of course, whenever we are grouping things within what we call a sample space, of permutations, we want to use parentheses to note that order actually matters. And lastly here, the archetypical example would be what we call an election problem. So let's say we had a group of 5 people, and out of that 5 people, we wanted to select who's going to be the president, who's going to be the vice president, and who's going to be the treasurer, okay? Now, of course, if the first person that we pick, we say the first person that's picked, he's the president. The second person that's picked, he's a vice president. The third person that's picked, he's a treasurer. It matters if I select Alfred first or if I select Bob first or if I select Deanna first, okay? Versus with combinations here, we'll see that that's not necessarily the case. So again, we know that with permutations, order matters. Here is the formula for it. And we know here that order matters basically means that in this example, 1, 2 is not the same as 2, 1. So let's go over to combinations now. So in combinations, we're doing grouping when order does not matter. So what does that mean here? So that means that if we list 1, 2 in a group, and then we list 2, 1 in the group, that's equivalent. It's the same thing, okay? So what we see here in combination is that all of the perceived repetition that is here, okay, is actually taken out here because this is looked at as the same thing. And this is also noted in the actual formula for a combination. If you notice here, our formula for this is combination of n things grouped or taken r at a time. And this is an alternate notation for it. But here you notice that we have an r factorial in the denominator that is not present here in the permutation formula. The reason for that is that r factorial is taking into account all of the repetition, or 1, 2 being the same as 2, 1. It's going ahead and getting rid of that in the actual calculation of the combination of n things grouped r at a time, okay? And like you see here, we use the set brace notation whenever we are talking about combinations of things. And lastly, the archetypical example of that would be the committee problem. And so a committee problem will look something like this. We have 5 people in the group, just like how we had when we did the permutations, but now we want them to be on an advisory board committee, okay? So if you know anything about committees, you know that each person that's on a committee pretty much has equal weight as far as voting rights and power and such. So it doesn't matter whether you pick first on the committee or you pick last on the committee. Whether you pick first or last really doesn't matter. We know that with the committee, everyone has equal weight, so the order in which you're listed really doesn't matter. And so that's why the committee problem is sort of the archetypical example of combinations. So now we've talked about permutations, we talked about combinations, and now what we want to do is get a concrete example to kind of show you the real difference in between a permutation and a combination. And case in point, what I want to do is basically show you that with a permutation, if we're trying to group, let's say, 5 things grouped 2 at a time, we will have more of these particular arrangements than we would if we had the combination. And that's mainly because of this r factorial that's here. And so next we're going to do an example that's going to explicitly show us that. So now let's do the example where we are going to take the permutation of 5 things grouped 2 at a time and the combination of 5 things grouped 2 at a time. And let's explicitly list their sample spaces so that we can see really what is the difference in between a permutation and combination as far as grouping is concerned. So if we look here, we want to do the permutation of 5 things grouped 2 at a time. So let's say our 5 things are 5 people. So let's just say here that we have Alfred, Bob, Carly, Diana, and Eve, okay? So let's say we have these people, and we'll call them A, B, C, D, and E for short, okay? So if we're going to do that, let's say that we want to take these 5 people and put them in groups of 2, okay? Well, since order matters, of course, we're going to use parentheses for that. And so I'm going to take Alfred first, and we're going to pair Alfred up with Bob, and then with Carly, and then with Deanna, and then with Diana, and then with Eve, okay? So we start off with A goes with B, then A goes with C, A goes with D, and then A goes with E. And of course, I'm not pairing A with A because we're not going to pair anyone with themselves, okay? So we started here at A, now we're going to move and pair everyone with B now. So if we go with B, We have B paired with A, B paired with C, B paired with D, and B paired with E. Continuing on, we have C with A, C with B, C with D, and C with E. Okay? So that's what happens when we move here. Okay? Now we'll go ahead and finish this out. So D will go with A, D with B, D with C, and D with E. And then we will do E with A, E with B, E with C, and E with D. Okay? And so if we look at this, all of these particular groups are unique when it comes to a permutation because order matters. So if we count how many of these unique groups that we have 1, 2, 3, 4 columns and 1, 2, 3, 4, 5 rows. So we know that permutation of 5 things grouped 2 at a time would just be 4 times 5, which would be 20. Okay? So we see when order does not matter, when order matters, that the permutation of 5 things grouped 2 at a time is 20. Now let's move on over to the combination. So for the sample space for the combination, we're going to do the exact same thing. Okay? I'm not going to recreate the wheel, but instead of using parentheses here, we're going to use set notation braces. So I'll just go ahead and rewrite everything in that now. Okay, so here you see we're writing the exact same thing, but we're writing it with set notation instead of the parentheses. And so I'll continue on and list all of this. All right, and so we're done listing our proposed sample space for the combinations. Now, remember that for combinations, we see that order does not matter. So something like A, B in a group is the same as B, A in a group. And note, since we know that combinations order does not matter, anything that we see repeating, we can just go ahead and eliminate it. So here, we see the group with AB, so the group with BA will be deleted since it's a repeat. We have AC, and so CA is a repeat. AD, so DA is a repeat. AE, so EA is a repeat. We move on to here, we have BC, so CB is a repeat. BD, so DB is a repeat. BE, so EB is a repeat. CD is here, so DC is a repeat. CE is here, so EC is a repeat. And DE is here, so ED is a repeat. And after we take out all the things that repeat, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this tells us here that the combination of 5 things grouped 2 at a time, alternatively written this way, is 10. Okay? And please do not mistake this being 5 times 2 is 10. because it does not always work that way. Okay. So with that, we've discussed permutations, combinations in a more concrete way where we've listed out a sample space. And now you see why indeed for the same N and R, a permutation would have more groups than a combination.